product, not that important as long as you know the basics. So how KEQ relates to Q, how KEQ relates to forward and reverse rate constants, and how to determine those rate constants only from experimental data, right? So remember, zeroth order is concentration of A as a function of time, is linear, first order, second order, etc. You need this data or you don't know what the order is.
And solids and solvents are equal to 1 in the reactant quotient, correct?
That's right. So if you have something like NaCl solid goes to, let's say, plus water, goes to Na plus, aqueous, plus Cl minus, aqueous, plus water, of course, because this has to be balanced. That's in the liquid. Q equals concentration of sodium over concentration of chloride, because those are both in the aqueous phase. And then these are all 1, right? 1. So it's just concentration of sodium times the concentration of chloride is Q. And so you know how that relates to KEQ, and you can determine if the reaction's at equilibrium or not by comparing Q versus KEQ. So yeah, solids, liquids, solvents, it's all 1 in the reaction quotient. Gases, we have partial pressures, remember, they're a good stand-in for concentrations, things in aqueous phase, those are all in the reaction quotient. Yeah?
Should we know how to use Q and KEQ to find pH?
Was pH on the review sheet? No. No pH calculations, I guess. I don't think. I'd have to go check the final that I just wrote today. So, but no, I don't think there are any pH questions because there wasn't on the review sheet. Mm-hmm.
For that oscillation chart, we had, I think it was the second test, with all the lines and the imaginary lines.
Yeah.
Review that for.
Sure. So the most important part about that chart is you have, I think it was the permittivity or the dielectric constant decreases as frequency increases. So this will be 10 to the 15th, this is 10 to the 7th. So the important part about this chart is that the real part of the dielectric constant is greater, so this can be 20, or let's say 20. And then as you increase the frequency, and this is the frequency of the oscillating wave, right? So this is the frequency of this oscillating wave that you send in to hit some molecule. At low frequency, you're going to have very big response of this molecule, and that gives you a high dielectric constant or a high permittivity. At very high frequency, that field is oscillating very quickly, and so you're not going to give this molecule a lot of time to respond, and so that lowers the dielectric constant or the permittivity. And the reason that is that, say at very low frequency, this dipole can turn very easily, right? So you have dipole down here, here you have electronic transitions, and so if you can access the dipolar motions of the molecule, that gives you very high real part of the permittivity. If you're only accessing electronic transitions, that gives you very small part of the, a small value for the dielectric permittivity. And so this is the important part about this chart that you should remember. And so remember, this is refractive index, dielectric constant. You had a question on your exam about the decreasing dielectric constant with increasing frequency. So let's say at 10 to the 7th, if I have two molecules, one has a dielectric constant of 20, one has a dielectric constant of 10, Which one has a greater dipole moment, would you think? Which one has a larger dipole if, let's say, A has a dielectric constant of 20, B has a dielectric constant of 10. Which one has the larger dipole in the molecule? 20, right? The refractive index, larger dipole oscillating, that's going to give you higher refractive index. Or I could say, you know, maybe B is 2. I could ask you, what's going on if one molecule has a dielectric constant of 20 at 10 to the 7th frequency, and the other molecule has a dielectric constant of 2 at 10 to the 7th, which one is polar, which one is nonpolar? 20 is polar, right? Because it has much higher contribution to the dielectric constant than B, which is probably nonpolar, so the dipole contribution is low, or 0. What about out here at 10 to the 15th? Say I have something with a molecule D has a dielectric constant of 10, molecule C has a dielectric constant of 2. Which one's more polarizable, D or C? D, right? More polarizable is always going to have higher permittivity, higher refractive index, higher dielectric constant. Remember, all of these are the same as polarizability, or they trend the same. So in this case, A and D would be polarizable. Let's say more polarizable. C and B is less polarizable. That's the important part of it. Yeah.
Can you touch on how polar a molecule is relates to polarizability and the differences?
So, yeah, so let's just talk about the difference between polar and polarizable. It's hard to tell exactly, well, let's just talk, what's a polar molecule?
Molecule that has a dipole?
A molecule with a permanent dipole, right? So is CO2 polar?
Yes. No.
No, because it's symmetric, right? Is CO2 polarizable? Yeah, no problem. All molecules are polarizable, right? Because all molecules have dispersion forces. So remember, for something to be polar, like acetic acid, it needs to be asymmetric and it needs to have a difference in electronegativity. And so you have some sort of polar molecule here. We know that iodine is nonpolar, right? It's perfectly symmetric. But all of these molecules are polarizable. What happens when you bring a dipole close to them? And so it's hard sometimes to tell the difference between the polarizability of something like acetic acid versus CO2. So I don't know which one is more polarizable, unless you know something, say, about the boiling points or the freezing points or something like that, right? We know that acetic acid has dipole-dipole forces. That still doesn't quite explain the polarizability. We need a chart maybe for the dispersion forces, and that would tell us which one is more polarizable. But remember, polarizable is, well, all molecules are polarizable, but that's the instantaneous induced dipole. So polarizable and induced dipole go together. Polar is something where you have the permanent dipole in the molecule. Yeah.
I know it increases polarizability, but what decreases polarizability? Or is there anything that explicitly that does or doesn't?
Yeah, so if you increase the electronegativity, that will decrease the polarizability, right? So if you have something like CF4 versus CH4, we know that F has very high electronegativity, right? So the polarizability of this thing is going to be lower than the polarizability of this thing, right? I mean, it's a little bit of a toss-up because there's certainly more electrons in fluorine. So maybe if we compared, maybe this isn't a perfect comparison, but maybe if we compared carbon tetrachloride to carbon tetrafluoride, which one is more polarizable?
Tetrachloride.
Yeah.
Chloride, right? So when we increase the electronegativity, the polarizability is going to go down. So which one's going to have the higher refractive index?
Tetrachloride.
Chloride, right? So this is higher polarizability, higher dielectric constant, higher refractive index. Yeah.
Is it kind of like something that is more polarized? It is have less polarizability.
That's not always the case. So I don't want to say that since this one is more polar, it's got less polarizability. In
Okay.
general,
For example, you have these two.
well, are either of these polar? No, neither of these are polar because they're symmetric, right? So think about the I mean, what matters is the electronegativity. Now this bond is polarized, right? So this bond has electrons that are more attracted to fluorine and less attracted to carbon. But since the overall molecule is symmetric, that all cancels, all those strong polarized bonds cancel each
I
other out.
want to just ask you this bond, the bond between carbon and the fluoride. The one bond, if it is more polarized, it is less polarizable, right?
That's true, yeah. So if you have very high electronegativity difference, so you have high electronegativity between, difference between fluorine and carbon, this bond is less polarizable than this, where these are closer in electronegativity. But think about the overall molecule. So I won't ask you whether carbon tetrachloride is more or less polarizable than acetic acid, because it's hard to compare something with a permanent dipole versus something that doesn't have a permanent dipole. But know the rules for when we change from high electronegativity to low electronegativity and things like that for polarizability. Or we do something simple like compare hydrogen versus nitrogen. You know, which one is more polarizable, which one has higher van der Waals forces, things like that. Which one has higher van der Waals forces, hydrogen or nitrogen?